Managing Tables and Indexes, Part 2 of 2. Now that we know a thing or two about creating tables and using data types, it's time for us to learn how to make those tables run quickly from the perspective of executed queries. And that deals with, sure enough, the index. Therefore, we're going to begin this nugget with a consideration of what indexes are and how they help speed up data retrieval in MySQL tables. Frankly, indexes are a key component of any relational database management system. Once we have the conceptual foundation down, as our habit would dictate, we'll log into MySQL and create and use one or more indexes. Now, it's one thing to feel like your server's running faster and to feel like your queries are being returned a little bit faster. It's another thing to actually verify index operation. I'll introduce you to a new SQL keyword called explain that enables us to view under the hood or behind the curtain to see exactly what the MySQL Query Optimizer is doing as far as leveraging indexes. Let's get started. What are indexes anyway? Formally defined, indexes are separate data files that greatly enhance data retrieval in MySQL or any RDBMS. The operation behind indexes in general uses an algorithm or a technology called B-tree. Now, B stands for either balanced tree or binary tree. It depends on who you're talking to and what specific school of thought they come from in relational database design. But the basic functionality of a B-tree index works as follows. Let's say we have a table called employees, and we're building an index that's keyed or mapped to the employee ID column. Let's say, moreover, we have 100 employees in said table. Now, what happens when we build an index keying on the employee ID column? Well, behind the scenes, MySQL is going to break that data into a number of pages and splitting those row pages in half. That's where you get the idea of the balanced tree or the binary tree. We have this what's called bilateral symmetry here, such that the first collection of pages will be split such that rows 1 through 50 would be in one page, and then 51 through 100 in another. Now, those pages actually contain pointers to further pages. In MySQL index nomenclature, we have what's called the root index page, the intermediate level pages, and then finally the leaf level pages. Ultimately, we get down to a more manageable size such that, and just in the simple example, we've got pages that contain 25 rows each. Now, how does this speed data retrieval? If we wanted to do a select against this employees table, and let's say we only wanted to see employee ID 10 through 20, as long as MySQL was making use of this index, I hope you can see immediately that because of the way the B-tree is structured, the MySQL Query Analyzer can ignore all of these pages over here that aren't relevant. The Query Analyzer knows exactly how to hopscotch through these pages to get to the relevant rows and then return that data to you, the user. Now, obviously, that's going to involve a big speed increase because normally what happens when a relational database system does query retrieval without an index, it performs what's called a table scan or a row scan. So if we didn't have this B-tree index defined on the employee table, and we were running a select such that we wanted to see only employees ID 10 through 20, MySQL would have to go through all of the pages of the entire table, row by row by row by row, until it gets back the relevant IDs. Consequently, I hope you can see here graphically and in a plain fashion how indexes speed up data retrieval because the MySQL parser or query analyzer has to look at only a subset of those pages instead of all of them. Some notes about indexes in MySQL 5.x. As nice as indexes are, and they really are, in most cases they're going to allow queries to run orders of magnitude faster than if the tables had no indexes. There are some gotchas that you need to be aware of. One is disk cost. When you create an index, you're effectively doubling the size of the table, at least as far as the columns that you're keying on in that table. In other words, indexes are actually materialized collections of data pages. For instance, in the MyISOM engine, you'll remember that each table has an MYD file that contains just the raw rows. And once you build an index, each index picks up the extension MYI. And as we're going to see in the demo, sometimes your MYI file can actually exceed the size of the associated MYD. Therefore, you need to keep disk cost in mind and avoid over-indexing for that reason as well as for performance. Now, performance can be hit because, frankly, sometimes for some select statements, a table scan makes more sense than an index. If you were running a select star or a select splat, as the character is sometimes called, against a table, there we could do a table scan just as well because the star denotes all columns and all rows. So in that case, I would hope that the MySQL Query Optimizer is performing a scan and not an index seek. On the other hand, for highly selective select statements, where we're running selects against certain columns, we're filtering with the where clause, and sorting with order by, their indexes really can come to the forefront, like I said before. But again, you need to keep performance in mind and not over-index. Don't create too many indexes, and also keep your index keys short. Let's take a look at some best practices. Create indexes on frequently searched columns. That's hopefully a no-brainer. Now, MySQL behaves similarly to Microsoft SQL Server inasmuch as when you attach the primary key constraint to a column, MySQL will automatically create an index that keys on that value, on that column. Now, when I use the term keys, I'm talking about ordering the rows in the table based on that column value. Therefore, when you're creating an index, you're not only thinking of, now what columns from my table are most likely to be searched on, but you also want to make sure that your key columns have what's called a high cardinality. In other words, a high level of uniqueness and discreteness. Because remember, the index simply takes those column values and puts them in a specified order and creates that B tree structure for easier lookup. Now you can force uniqueness in an index by putting on the unique constraint in your create index statement, but you don't have to have your index be unique for every column. In other words, you might decide to create an index on a column that has, say, null values in it. And as far as MySQL is concerned, null values are not evaluated equally. In fact, you could even have null values in an index in which you attach the unique constraint. That's a big difference between MySQL and SQL Server, in terms of MySQL does not assume that two column values, two rows in the same column that have null attached to them, in other words, there's nothing stored there for that column, that they're not necessarily equal. You see what I mean? Finally, when you decide, or if you decide to build an index on string columns, which could be very useful. I mean, last name doesn't have a great deal of cardinality, but if you're running an HR employees database and you're constantly doing lookups on last names, you'd probably want to create an index that keys on last name. When you do this for string columns, in order to save yourself some disk cost and performance, you can specify what's called a prefix. And what that'll do is simply take the first X number of characters in that field and build the data page index, the B tree index, based on those characters. That's going to increase performance because MySQL Query Optimizer doesn't have to read the entire string value. It can just look at the prefix. And as long as you make your prefix long enough to ensure as much cardinality as possible, you're still going to get good performance on those lookups at a reduced disk cost. Types of indexes in MySQL 5.x. Here's the full list. There's 5 types of indexes, and the things you need to understand about these for your exam are as follows. Number 1, these indexes are engine dependent. I would suggest you hit up the MySQL reference manual for specific guidance here, but the take-home messages for the exam are that full text indexes, unfortunately, are limited to the MyISOM storage engine. Therefore, if you have character fields for which you need to perform quote-unquote fuzzy lookups, where you need to actually index every value in every row that uses a text or character-based column, then for that table, I'm afraid you're going to be restricted to using the MyISOM storage engine. The other indices, or indexes, however you want to pronounce it, are used or capable of being used with MyISOM or InnoDB. But as I said, you can consult the reference manual for the specifics. This is really the take-home message for the exam. Another take-home message is the primary key index. As I already said, you get an index created that's keyed on that column automatically, or automagically, as an old colleague of mine used to say, as soon as you add this constraint to a particular column. Now, as we'll see in the next whiteboard in the demo, you can actually create an index in a couple of different ways. You can actually use the create index DDL statement, or you can add an index to an existing table using the alter table statement. Now, the primary key index cannot be created with create index. The only ways you can create this generated primary key index is to, as I said, specify the primary key constraint in a create table or an alter table statement. Okay, so keep that straight. The other kind of index is unique, non-unique, full text, and spatial. You can do that either in your table statement, or you can use the create index DDL command, as we'll see as we go along. We've talked about unique and non-unique. This forces row-level uniqueness on the key column. Non-unique is actually the default. And spatial indexes are a special type of index that's used for mathematics and science and dimensional analysis applications. In conclusion, if you decide you do need to move from one storage engine to another, you know how to do that by now, don't you? We would simply run the alter table command with the engine clause to specify our destination engine, whether that's Falcon or MyISOM or InnoDB or whatever. Let's again review the syntax for creating indexes. One way to do it, if you know at creation or design time of your table, you can add the index clause to a column definition of the create table or alter table statement. Alternatively, with the exception of the primary key index, you can use create index to build that index. And how that would work is simply this. Create index, and then optionally you can provide a name. I'll just say iname here. Then you'd specify on the table, and then after that, in parentheses, the name of the key column. So let's say we wanted to create a character-based index based on the last name column. And moreover, because this is a character-based column, we'll make use of prefixing to save ourselves some disk space. We can throw that in parentheses too, so you wind up with double parentheses at the end of the statement. So in summary, this statement would create an index called iname on the employee table that keys on the column named last name, and moreover, we have a prefix length of 10 characters, so only the first 10 characters of each row will be included in the index. When you're finished with an index, or if you've decided that an index is hurting more than it helps, and frankly that can happen sometimes, that's why it's important to monitor your MySQL query optimizer to make sure that it's actually functioning well. We can use either the alter table statement to drop an index, or specifically the drop index command. Verifying index operation. The MySQL Query Optimizer is that component of MySQL Server that's responsible for efficiently returning query results. And it is hoped that the Query Optimizer will make intelligent use of any indexes that you've attached to tables in question. Now, how can you tell if the Query Optimizer is working? Well, one way, just empirically, is to run your select statements against the unindexed table and see the time stamp that MySQL gives as far as how long it takes to satisfy the query, deploy an index, and then rerun those same selects and compare your results. Again, depending upon the type of index and the type of queries you're running, you'll see a dramatic speed improvement when you're using indexes. By the way, something I failed to mention earlier that I'll mention now is that at least the two main storage engines with which we're concerned in this course, MyISOM and InnoDB, allow you to key on up to 16 columns. When you build a column that keys on more than one column, you're creating a composite index, or an index that's using what's called a composite key. so that the rows will first be sorted by your first key column and then second sorted by the second key column. And 16 is a pretty high upper limit. If memory serves, that's also the maximum number of key columns that Microsoft SQL Server 2005 and 2008 support. Now, does that seem arbitrarily high? Bottom line is, wider keys involve more CPU cycles, more memory. You better have a pretty beefy machine and have a really good reason, in my humble opinion, to create a wider key. Narrower keys are faster. However, your mileage may vary as a DBA. Besides the empirical format, just to see and feel how fast queries run once you've deployed indexes, you can actually peer behind the curtain and display the actual query execution plan that the MySQL Query Optimizer is using. And for that, you'd use another MySQL extension to ANSI ISO SQL called explain. And we would simply prepend the explain statement to our select, and instead of running the statement and giving us a row set in response, we'll see a small table of metadata that tells us exactly what MySQL did to resolve that query in memory. This can be very helpful in terms of helping us tune our indexes, and by tune I mean A, should we use an index for a particular table and for particular types of queries, or if so, how should we structure our key, column, or columns, and finally, can we rewrite a query to make more efficient use of index X or index Y? In this demo, we're going to create a simple table that contains a single column with lots and lots of rows. And the reason for this is simple. Having a table with a single column with lots of rows gives us fertile ground for creating indexes and comparing the speed of data retrieval both with an index and without. We'll finish this demo with a flourish by using the explain statement to go under the covers and see exactly how the MySQL Query Optimizer is satisfying these queries. In this demonstration, we're going to work with indexes in MySQL 5. And we're on Ubuntu Nugget here. We'll start off by opening a terminal window. You see I'm logged into MySQL. I'll do a select user to verify that I am logged in as the root MySQL user. And I'll show databases here to show you that I've created a database called store that's going to serve as the repository for our test table. So let's use store, and we're going to build, as I alluded to in the prefix to this nugget, a single table that contains a whole bunch of rows, and we're going to compare query performance both without an index and with an index. So therefore, let's run create table, and I'm going to call this table sales. It's going to contain just one column. Whoops, I fat-fingered that, so I'm going to back out, and let's try that again. Create table sales, and we're going to have one column, as I said, called revenue. And this is going to use the decimal data type. Remember, decimal is best for currency. And I'm going to put 1,000,000 rows in this table. So we want to define our decimal scale to accommodate at least that number of characters. Let's see, 1,000,000 is 7 characters, 2 decimal points is 9. Let's just call the scale 10 and the precision 2 because we might have $99.99. So this is saying the column can hold a maximum of 10 characters, including the decimal points, and we're storing 2 decimal places here. Good enough. So we can close things out and create that table. So if we now show tables in that database, we have sales. Remember also, just to review, you can always review how a table was created by using show create table, in this case sales, and that'll come back with the SQL that I used. And this is good. I'm glad I ran this because I wanted to verify that we were using the MyISOM storage engine here, and sure enough we are. Now, let me come out into the file system and show you where I am. On Unix Linux systems, you'll recall that the default data directory is var lib mysql. In Windows systems, it's going to be your MySQL, your program data directory. And what I've done is actually gone into the store database. If I come up one level and run a directory listing, you'll recall in the root of the data directory, we have a folder or a directory for every database defined on the instance. I'll come back into Store and run a directory listing there, and you'll see our data file, sales.myd, our table structure file, our FRM file, and we do see a sales.myi file that's just tiny, 1 kilobyte. It's an empty file, I would bet. The data file is 0 because it has no data in it. I have a file called sales.txt, and this is a simple text file with a single column of data in it. Matter of fact, I'll use the tail command to show you the last 10 or so values in the file. We go all the way up to 999,991, all the way to 1,000,000. So there's actually 1,000,000 rows in the sales.txt text file. We're going to import that and slam dunk it into our table in just a second. But first, let me come back to MySQL and let you know of another command that you should know. It's show index. You can run show index against any table. I'll run it against sales now. And you see that we do not have any indexes defined for the sales table, even though the MyISOM engine created, I guess you'd consider this a shell or a prototype.myi file. It's a little bit misleading, I think you'd agree. All right, therefore, the next task on our agenda is to take this sales.txt file and slam dunk it into our sales table. Now, it's important that your external file have the same exact name as the table that you want to slam dunk into. And we're going to use an external tool now called MySQL import, and we'll authenticate as root user. We're going to spend a whole nugget on data import and export later in the course now, so just roll along with me here as we use this tool. And what we're going to do is specify the target database, which in this case is store, and then we're going to specify the name of our file, which exists in the current directory. So we'll put in our MySQL root password, and it looks like it took it. Store.sales now has 1,000,000 records in it, 0 skipped, 0 deleted, 0 warnings. So, okay, it looks like we're good. So to verify that, let's come back and run a select star from sales. And it's going to take a little while to iterate through all 1,000,000 rows. So I'm going to pause the video while it does that. Okay, so we got our row set back, and it tells us how long it took for that to happen. Now, this 0.73 seconds is not how long it took to display to standard out. It took actually 30 or more seconds to display all these rows on my terminal. The 0.73 seconds is how long the query optimizer in MySQL took to resolve that query. And you might think, well, wow, that's just a little bit longer than half a second. That's great, isn't it? But it's not great, and there's a few reasons for that. Number one, there's just 1,000,000 rows of very simple, numeric, already sorted data. Number two, I'm the only user logged on to this server. Imagine if 10 users were trying the query at the same time. What would happen then? And number three, I happen to be recording this nugget on a pretty powerful PC that's got lots of CPU power and lots of RAM. In a production environment, Linux machines traditionally don't require all that much hardware, so your mileage may vary. We're going to see that this 0.73 seconds should go down to 0 seconds once we've attached an index. Now, a way to get a quick row count on a table would be to run select and then against the count function. So we could say select count star, which means count all rows from a particular table. So that's another nice little function I'd like you to put in your pipe and smoke or file away in your pocket, however you want to say it, that you can get a quick row count from a table by selecting against the count MySQL function. And sure enough, we have 1,000,000 rows in this, and running a select splat is pretty darn slow. So the next question, of course, is how can we build an index? Well, we can use the alter table statement, or what I'm going to choose to do now instead is to use the create index statement to build an index on this table. And I'll just call this index, well, you'll remember back in the file system, there's already a sales.myi. I'm going to create a sales2 name for this index, and we're going to put it on the sales table. And then in parentheses, we're going to put our key column, which in this case is just the one column revenue. You see how that works? So we're building an index called sales2 on the sales table that's being keyed on the revenue column. Now you'll notice that the system paused for a second. It took almost 2.5 seconds to create that. And the reason for that is because number one, MySQL has to run the query again to get hold of all those values. And number two, we need to provision and populate a file that stores the values sorted on that column. So again, if we run a directory listing here, we'll see now our sales.myi file. We see our sales index file now is 12 megabytes in size. It's actually larger than the associated MYD file. This is proof the fact that these indexes do have a disk space footprint, so you want to be careful and selectively index your tables for maximum performance. Now, of course, we can show index from sales, and the response we get, actually, I'm going to throw in \G to make the rows come back a little bit easier to read. It tells us that on the table sales, we have one non-unique index. The key name is sales2. The column name is revenue. The cardinality is the maximum number in that row set, and so on. And it tells us significantly the technology used for this index is B-tree. The name that we give to the index is stored in the key name column in that index definition. Alrighty, well, how about if we run another select star from sales? Do you think we're going to get a performance boost? Interestingly, that return took longer to process than without the index. How about if we do something a little bit different? How about if we say instead of select star, we'll explicitly state the name of the column, and we'll throw in a where clause where the revenue is less than 50,000. All right, 0.09, that's better. Let's run it again. 0.1 second, 0.02 seconds. So we're getting a little bit better performance there with our index. That's cool. I'm glad to see that. How about if we try select star from sales? Well, let me use uppercase here. Old habits are hard to break, right? Where revenue is greater than, let's say, 10,000, and revenue is less than 20,000. 0.02, let's rerun that query, 0.02. So that's pretty close to zero. I have to tweak and tune these things to make them run better. And you'll also remember that explain is going to allow us to peek under the hood and see what's going on. So why don't we say explain select star from sales where revenue is greater than 900,000. And actually, to make that look a little bit better, let's do a \G so we can parse the results a little bit easier. And to make sense of this, we have our select type. This is a simple select. The table is sales. The type shows us what kind of join or joins are being used. This could be system, it could be ref, it could be range, it could be index. Here it's a range query. We're looking at all values where revenue is greater than 900,000. But the real meat and potatoes, what you want to see, are these two columns here. Possible keys on which to satisfy the query and key. Now, key and keys in this situation are synonyms for indexes. And you'll remember the name of our key in our index was sales2. And then finally in the extra column tells us that we are in fact using the index, and it gives us the row count of how many rows specifically were brought back. And we even have the key length, 6 characters in this case. So that's a little bit on explain. If you're coming from Microsoft SQL Server and you've looked at estimated and actual execution plans there, obviously you've got a much prettier picture than you do here on the MySQL client. I do want you to know that you can download and use another tool from the MySQL team called MySQL Monitor that can give you more robust information than what we're seeing. That said, I'm sticking as closely as possible to our certification objectives, and you absolutely need to understand the explain statement and know why and where it's used in MySQL 5. To end this demo, why don't we drop the index called sales2 from the sales table. To do that, we'll say drop index, then the name of the index. We know that's sales2 in this case. We don't use from, we use on the name of the table. Good. So it tells us that million rows were affected, million records, no duplicates, etc. So if we come back to the file system and run another directory listing, we see that our sales.myi has gone from being 12 megs in size down to being 1K in size. Note, though, that the myi file is retained in the database directory. So therefore, if we do a show index from sales, we do in fact get an empty set. So if we try our explain statement again on a previously done query, we see that there's no possible keys, there's no index to be used, and we do use the where clause, and in this case tells us there's one row in the set. And if we just run the select statement straight away, we see that it took 0.33 seconds for the query optimizer to satisfy this query. Number one, we've been running the query a lot, so the execution plan, as much as possible, is still in memory. But number two, you'll remember that when we had an index, we were dealing with 0.0 values. So we still have a noticeable increase in speed from using an index to not using an index and back again. Managing tables and indexes, part 2 of 2 review. I hope in this nugget you've picked up some useful information regarding indexes and that you'll be able to apply your new skills in your real-life production MySQL environments. To review, we started with an architectural or theoretical overview of what indexes are, how B-trees operate, and some of the best practices regarding index usage in MySQL 5. We then broke out the SQL and built indexes and tested them to verify speed increases on data retrieval. And finally, we looked at the query optimizer component of MySQL and used the explain keyword to see exactly how those queries are getting resolved and to guide us in further performance tuning. I hope that this has been informative for you, and I'd like to thank you for viewing.